I'd like to say a few final words about supervised versus unsupervised learning. In both cases, you're given data, but in one case, you have labeled data, in another, you have unlabeled data. The supervised learning paradigm is the dominant paradigm in machine learning, and a vast amount of papers being written about it. We talked about classification and regression, and different methods to do supervised learning. The unsupervised paradigm is much less explored, even though I think it's at least equally important, possibly even more important. Many systems can collect vast amounts of data, such as web crawlers, robots. I told you about Street View. And getting the data is cheap, but getting labels is hard. So to me, unsupervised is the method of the future. It's one of the most interesting open research topics to see whether we can make sense out of large amounts of unlabeled or poorly labeled data. Now, in between, there are techniques that do both, supervised and unsupervised. They're called semi-supervised or self-supervised, and they use elements of unsupervised learning and pair them with supervised learning. Those are fascinating by their own rights. Our robot Stanley, for example, that won the DARPA Grand Challenge, used its own sensors to produce labels on the fly to other data. And I'll talk about this when I talk about robotics in more detail. But for the time being, understand that the paradigm supervised and unsupervised span two very large areas of machine learning, and you'll learn quite a bit about it.
The first logic we will consider is called propositional logic. Let's jump right into an example, recasting the alarm problem in propositional logic. We have propositional symbols B, E, A, M, and J, corresponding to the events of the burglary occurring, of the earthquake occurring, of the alarm going off, of Mary calling, and of John calling. And just as in the probabilistic models, these can be either true or false. But unlike in probability, our degree of belief in propositional logic is not a number. Rather, our belief is that each of these is either true or false or unknown. Now, we can make logical sentences using these symbols and also using the logical constants, true and false, by combining them together using logical operators. For example, we can say that the alarm is true whenever the earthquake or burglary is true with this sentence. E or B, with parentheses, implies A. So that says, whenever the earthquake or the burglary is true, then the alarm will be true. We use this V symbol to mean or, and a right arrow to mean implies. We could also say that it will be true that both John and Mary call when the alarm is true. We write that as A implies, parentheses, J and M. And we use this symbol to indicate an and. So this upward-facing wedge looks kind of like an A with a crossbar missing. And so you can remember A is for and, right, where this downward-facing V symbol is the opposite of and, so that's the symbol for or. Now, there's two more connectors we haven't seen yet. There's a double arrow for equivalent, also known as a biconditional, and a not sign for negation. So, we could say, if we wanted to, that John calls if and only if Mary calls. We would write that as John is equivalent to Mary. When one is true, the other is true. When one is false, the other is false. Or we could say that when John calls, Mary doesn't, and vice versa. We could write that as John is equivalent, the double arrow, to not Mary. And this is the not sign. Now, how do we know what the sentences mean? A propositional logic sentence is either true or false with respect to a model of the world. And a model is just a set of true-false values for all the propositional symbols. So a model might be the set B is true, E is false, and so on. We can define the truth of a sentence in terms of the truth of the symbols with respect to the models using truth tables. Here are the truth tables for all the logical connectives. What a truth table does is list all the possibilities for the propositional symbols. So P and Q can be false and false, false and true, true and false, or true and true. Those are the only four possibilities. And then for each of those possibilities, the truth table lists the truth value of the compound sentence. So the sentence not P is true when P is false, and false when P is true. The sentence P and Q is true only when both P and Q are true, and false otherwise. The sentence P or Q is true when either P or Q is true, and false when both are false. Now, so far, those mostly correspond to the English meaning of those sentences, with one exception, which is that in English, the word or is somewhat ambiguous between the inclusive and exclusive or, and this or means either or both. We translate this mark into English as P implies Q, or as if P then Q, but the meaning in logic is not quite the same as the meaning in ordinary English. The meaning in logic is defined explicitly by this truth table and by nothing else. But let's look at some examples in ordinary English. If we have the proposition O and have that mean 5 is an odd number, and P meaning Paris is the capital of France, then under the ordinary model of truth in the real world, what could we say about the sentence O implies P? That is, 5 is an odd number implies Paris is the capital of France. Would that be true or false? And let's look at one more example. If E is the proposition that 5 is an even number, and M is the proposition that Moscow is the capital of France, what about E implies M? 5 is an even number implies Moscow is the capital of France. Is that true or false? The answers are, first, the sentence, if 5 is an odd number, then Paris is the capital of France, is true in propositional logic. It may sound odd in ordinary English, but in propositional logic, this is the same as true implies true. And if we look on this line, the final line for P and Q, P implies Q is true. The second sentence, 5 is an even number, implies Moscow is the capital of France. That's the same as false implies false, and false implies false, according to the definition, is also true.